Miss, what is the sun made of?
Well, let's see. All right, so NASA says that it's 91% hydrogen and 8.9% helium in terms of the number of atoms. So let me ask you a question. How do they know that? How do they know there's helium and hydrogen in the sun?
They probably went into space, took some of the sun back to Earth, and like did chemistry on it.
Wait, isn't the sun like a gazillion degrees though?
Well, it's actually 5,778 degrees Kelvin, or since we're in America, we use Fahrenheit. That would be 9,941 degrees Fahrenheit, which is very, very hot.
What, so did they like just burn themselves when they went up there?
Actually, they didn't go up there at all. Sun is way too hot for us to visit, and no spacecraft or human has ever returned from the sun. Scientists have actually determined what elements are present in the sun from right here on Earth.
So they just looked at the sun?
Miss, my dad said you're not supposed to look at the sun.
Your dad is correct.
How can you tell what elements are in something just by looking at it? That doesn't make any sense. Like if I look at a fork, I don't know if it's nickel or iron or aluminum or whatever.
Well, the way that scientists determine the composition of stars is using something called spectroscopy.
Spectacles.
Yes, the Latin prefix spect means to look or see. And spectroscopy is the study of how atoms absorb and emit energy in the form of electromagnetic radiation.
Electromagnetic? Is that like electricity and magnets put together or something?
Well, it's kind of like that. So electromagnetic radiation are waves that are created as a result of vibrations between an electric field, right? So here we see the electric field in red and the magnetic field, the one that we see in blue. And if we look here, we can tell that they are perpendicular to each other, which means they're at a right angle. So these two fields are always together, always perpendicular to each other, and they travel through space at the speed of light. Actually, electromagnetic radiation is just the scientific term for light. Did you know that there's certain kinds of light that we can't see?
Like you mean like how we can't hear dog whistles?
Kind of like that. Yes, because dogs are able to hear outside the range of what humans are able to hear, but sound is different because light doesn't need a medium to travel through, right? Sound either travels through a solid or a liquid, but electromagnetic radiation doesn't need a medium, which is why it's able to travel through space. This is the electromagnetic spectrum. The wavelength determines what wave it is. So on the left, these are really, really, really tiny waves. And on the right, these are really, really big waves. And if you take a look, this tiny little piece here, we zoom in on it here, this is the only part of the electromagnetic spectrum that we are actually able to see. Fun fact, some animals like snakes are able to see this infrared light.
How exactly do scientists see the parts of the electromagnetic spectrum that we can't see with our eyes though?
Scientists have actually created machines that can see all of the wavelengths in the electromagnetic spectrum. Those machines collect information about the wavelengths emitted by stars by pointing telescopes into space. By analyzing the light that the sun emits, we can obtain a huge amount of information, including what elements are present. Essentially, all of the information we have about stars comes from the analysis of the light that they emit, including both the visible light that we see in the middle here and all the light that we are not able to see.
What do you mean by analyze the light?
Spectroscopy is the technique of splitting light, or more precisely, the electromagnetic radiation, into its constituent wavelengths, or a spectrum, as we call it. When white light goes through a prism, we see all the wavelengths of visible light in the spectrum from 400 to 700 nanometers. White light is actually a combination of all of those wavelengths, and the prism allows us to see them separately by spreading them out. This is called a continuous spectrum because all the wavelengths of visible light are present.
I still don't understand how that rainbow tells us what elements are in stars.
So white light has all of the colors of the rainbow in it, but light emitted by gases when they are excited only show a few special wavelengths. Each element emits a unique combination of wavelengths called its emission spectra, which is like a fingerprint for each element.
What do you mean excited? Are they like going to Disneyland or something?
Here we have the sodium ion in the ground state, and we are going to add energy in the form of heat in order to excite one of the electrons. So after absorbing the energy, one of the electrons is excited, right? It moves from a lower energy level up to a higher energy level. But if you've ever eaten too much candy and maybe had a sugar rush, you know that that doesn't last for very long. So the excited electron is going to release its energy as it falls back down to the ground state, and it releases that energy in the form of light.
So if it's like just going up and coming back down, then how are all the elements different from each other?
The wavelength of light that is emitted when the electron falls back down to the ground state depends on the distance it falls from the excited state. So because the spacing between orbitals in different atoms is different, the wavelengths of light that are emitted are different as well. So if we look here, we'll use hydrogen as an example. Starting at the second energy level, the electron is excited up to the third energy level. When it falls back down, it releases a wavelength of 680 nanometers. Do it again, goes from the second up to the fifth. From the fifth down to the second, that emits a wavelength of light that is purple instead of red. And one more time, from the second to the third, or the second to the first. And if we notice there, that wavelength that it emitted completely missed the visible spectrum. So when this is happening to many atoms at once, it creates a bunch of these wavelengths at the same time, which looks like one color to our eyes. Notice that some of the wavelengths being emitted, like we saw before, are totally missing the spectrum. This image only shows us the visual spectrum here. Wavelengths that fall to the left over here are way too short for our eyes to see. Wavelengths that fall to the right on this side are way too long for our eyes to see. So by viewing the light emitted by an excited gas through a prism, right? This here is us exciting the gas. We are running an electric current through it. Comes through here, goes through the prism, and it splits it up into its wavelengths. Once those wavelengths are separated, we can see that there are only a certain few wavelengths instead of the wavelengths we see in the continuous spectrum. This is called the emission spectra because the only lines that you're seeing are the wavelengths being emitted by the atoms. So let's say we're looking at the emission spectrum of some unknown gas. What we're able to do is compare that unknown gas to elements that we know the emission spectra to. So here I have mercury. Let's see if those lines match up. Some of them do, but in order to identify it as the element, all of the spectral lines need to match. So it's not mercury. Doesn't look like hydrogen or sodium. Looks like helium matches. So we had an unknown gas. We compared it to other emission spectra, ones that we know, and we were able to identify the mystery gas as helium. So those were just a few examples that we saw, but every single element on the periodic table has its own unique emission spectra, like a fingerprint.
Why does it show the leftover parts of the rainbow underneath it? It looks like if you put them together, then it'll make the whole visible spectrum.
So that is called the absorption spectrum, and you are correct. The absorption and emission spectra are just two separated parts of the same continuous spectrum. The center of a star in space is extremely hot, and it emits a continuous spectrum. However, in between the super hot star and us here on Earth, it's really, really, really cold. So when we look into space, we see the absorption spectra because cooler gases in the outer layers of the star absorb certain wavelengths of light, leaving dark lines on the continuous spectrum. To determine the elements that are present in a star, scientists compare the absorption spectra of the star that they're studying to the known spectra of the elements here on Earth. So let's give that a try ourselves. So let's take this star, for example. When we take the light that is coming from the star and we pass it through a prism, we break it up into its constituent wavelengths. And you notice down here, right, it's the entire rainbow, but some pieces are missing, right? Those pieces called spectral lines, those wavelengths were absorbed by the cold gas in between us and the hot star. So in order to determine what elements are present in that star, we would take the absorption spectra of elements and compare them. So let's take a look at hydrogen. We put them next to each other and see if any of the lines match up. So does it look like there's hydrogen in the star?
Yes, but not all of them.
Yes, right? Okay, very good. So if we look here, this one matches up, this one, this one, this one, but we're still missing a few of the lines, right? So when we look into space, look at stars, there's not just one element present in there. There's things mixed up in there. So what we have to do is take a look. Okay, so we know there's hydrogen in there, and then we ask ourselves, what else is in there? Okay, so we know hydrogen's in there. Let's see helium. Maybe helium's in there too. What do we think?
Yeah, I think so too.
Yes, all right. And it looks like the ones that are missing, right? So if I have hydrogen and helium, I can see that all my spectral lines are accounted for. Yes. Right, so here we can tell that there is helium and hydrogen in that star, which is exactly where we started. We're also in the sun.